Now the last experiment that we are going to try has to do with again negative feedback, which has been covered extensively in the first experiment. However, it falls in the power supply category, and it is one of the most important efficient linear regulator that is used today. Let us discuss what it is. Why the name low dropout comes into picture also. Linear regulator is definitely a feedback principle of a non-inverting amplifier with one supply being unregulated, the other being ground. We are deriving the reference from the unregulated supply. Let us say there is a circuitry, make it independent of supply temperature, etc. So the Vz is a reference which is constant, right? And if it is negative feedback like this, then we know that the gain of this whole thing is V0 is going to be equal to Vz into 1 plus R2, because it is V0 into beta. Beta is R1 by R1 plus R2, which is made equal to Vz, and therefore Vz into 1 plus R2 over R1 is what the output is going to be, and the load can be delivered current by this operational amplifier. Now we have to investigate the line regulation, which means how this remains constant at this value independent of the unregulated voltage, changing from a minimum to a maximum value. Okay, and what is the percentage change in the output voltage? That is called line regulation factor. And the load regulation is as the load current is varied from its minimum to a maximum, what is the percentage variation in the output voltage? These are two large signal parameters which you can measure for this regulator. And then the output impedance, which is a small signal parameter, it has to be measured at the frequency at which this is supplying power, right? So if it is supplying power to, let us say, a high frequency stage, it is at that frequency that you have to measure the output impedance. That output impedance should be low, so that other circuits which are deriving power from the same supply do not get the feedback from this particular high frequency circuit that you are using. So this gets converted to a high current operation by putting a current amplifier in the load. So output still remains the same as before. Only thing is, because of putting this N channel MOSFET here, the minimum voltage up to which, minimum unregulated voltage up to which this becomes functional, okay, keeps increasing as you keep on putting such cables. And therefore, what is the remedy for this? You can use, instead of N channel MOSFET, a P channel MOSFET like this. The moment you use a P channel for driving this, there is a gain coming into picture in the loop. Earlier this is a voltage follower, and therefore the gain remained same as A0. Here the overall gain increases by a factor of GM of this into RL. Okay, that means A0 GM RL is the gain. Not only that, since there is an inversion here, you have to now make this overall thing have negative feedback by connecting the positive of the operational amplifier. Now the advantage of this is this voltage can be made as low as you please. The difference voltage into the load current is essentially the power dissipated in the IC. So here it is large, okay, and here it can be made very, very small. That means this keeps functioning even when being unregulated comes very close to the regulated value that you desire. So this is the advantage of low dropout regulator. Okay, and you have to design the compensation scheme for the increased gain of A0 into GM into RL. Right? So you make sure that you make all the measurements of load regulation, line regulation, ripple rejection. Again, you assume that there is a ripple superimposed over the unregulated supply, which is normally at 50 Hertz or 100 Hertz if it is coming from the power line. Okay, and then how much of it gets transmitted to the output. That is what is called ripple rejection factor. Right? So make the measurement of all this. Ripple rejection is a small signal parameter. Output impedance is a small signal parameter. and the line regulation and load regulation are last in the current.